Artificial intelligence is no longer confined to research laboratories, technology companies, or teams of specialist programmers. It is increasingly becoming part of the everyday work of professionals, researchers, educators, business leaders, governments, and individuals. In this video, we will explore the foundations of artificial intelligence, how the technology evolved, and why large language models have changed the relationship between people and computers. This is part 1.1 of our series, Artificial Intelligence Explained: Foundations, Evolution, and Large Language Models. For most of computing history, people had to learn the language of machines. They had to understand programming languages, remember commands, navigate menus, and operate specialized software. Computers were powerful, but people had to communicate with them in carefully structured ways. Today, that relationship is changing. Modern artificial intelligence systems increasingly allow us to communicate with computers using natural language. Natural language simply means the ordinary written or spoken language that people use every day. Instead of writing software code, a person can ask, summarize this report, explain this data, translate this paragraph, help me prepare a presentation, or what are the major risks facing this project? A natural language interface is a system that allows people to interact with a computer through ordinary conversation rather than through formal programming commands. This is one of the most visible breakthroughs associated with modern AI. The transformation is not only that computers have become more powerful, it is that people can now access that power more directly. The interface has moved from code to graphical menus and increasingly to conversation. To understand the significance of this change, we will follow the development of AI from its foundations to its emerging future. We will begin by examining why AI has become transformative and what artificial intelligence actually means. We will then trace its evolution through machine learning and deep learning before introducing foundation models and large language models. Finally, we will explore how natural language changed human-computer interaction and how generative AI is beginning to evolve towards agentic AI. Agentic AI refers to systems that can pursue goals, create plans, use tools, and perform sequences of actions with defined levels of human supervision. Artificial intelligence has become transformative because four important developments have come together. The first is capability. Modern AI systems can analyze information, recognize patterns, make predictions, generate content, and support decisions. Pattern recognition means identifying recurring structures, relationships, similarities, or unusual features within data. A prediction is an estimate about a future event, an unknown value, or a likely result based on patterns found in available information. The second development is accessibility. People can increasingly use AI through natural language. This reduces the need for advanced programming knowledge and allows many more people to work directly with sophisticated computing systems. The third development is versatility. Earlier, computer models were often designed for one narrow task. A modern model may be able to summarize documents, answer questions, classify information, translate languages, generate software code, and support analysis. A model is a computational system that has been trained to identify patterns and use those patterns to produce an output. The fourth development is reach. AI can be applied across healthcare, education, agriculture, science, business, government, and many other sectors. These four developments, capability, accessibility, versatility, and reach, help explain why AI is increasingly viewed as a transformative technology rather than simply another software tool. This brings us to a fundamental question. What exactly is artificial intelligence? Artificial intelligence refers to computational systems capable of performing tasks traditionally associated with human intelligence. A computational system is a combination of software, data, and computing resources that processes information according to mathematical procedures and instructions. These procedures are often described as algorithms. An algorithm is a defined set of steps or mathematical procedures used by a computer to process information, solve a problem, or produce an output. The capabilities associated with artificial intelligence include learning, reasoning, language processing, pattern recognition, problem solving, decision support, and content generation. Learning in this context does not mean that a machine learns in the same conscious way as a person. It means that the system adjusts its internal numerical relationships after being exposed to data and examples. In an AI system, reasoning refers to using available information to examine relationships, evaluate possibilities, and generate a proposed conclusion or course of action. Decision support means helping people evaluate evidence, compare alternatives, and make better informed decisions. The final responsibility for important decisions should continue to rest with people. Content generation means producing new material such as text, images, audio, video, presentations, or software code. Artificial intelligence should therefore not be viewed as a mechanical copy of human intelligence. It is a broad field of computational capabilities that can support and augment human work. That broad definition is important because artificial intelligence is not one single technology. It is an umbrella term that includes many different approaches, systems, and model types. Rule-based systems use explicitly programmed rules and logical relationships. For example, if the temperature exceeds the safety limit, activate an alert. Predictive models use patterns in existing information to estimate a likely future result. They may predict sales, equipment failure, customer demand, or financial risk. Neural networks are computing models made up of connected layers of processing units. They are loosely inspired by biological neural systems, but they are not artificial versions of the human brain. Generative models create new content based on patterns learned during training. This content may include text, images, audio, video, designs, or software code. Language models are trained to process and generate human language. Multimodal models can work with more than one type of information, such as text, images, audio, and video. AI agents are systems that can interpret a goal, gather information, create a plan, use tools, and execute a sequence of tasks with varying levels of human supervision. A chatbot is therefore an application of artificial intelligence. It is not the complete definition of AI. Some AI systems predict, some classify, some monitor industrial equipment, some analyze medical images, some generate content, and some increasingly coordinate multi-step work. AI is a field, not a single product, interface, or application. One of the clearest ways to understand modern AI is to compare it with conventional software. Conventional software and artificial intelligence are both created through programming. The difference lies in how they produce results. In conventional software, people define the rules. The software applies those rules to data and produces an output. For example, if an invoice is overdue, send a reminder. The condition is clearly defined and the action is predetermined. This approach works well when the task is stable, repeatable, and clearly specified. A machine learning system works differently. Instead of being given a separate rule for every possible situation, a machine learning system is trained on data and, in many cases, examples with known outcomes. It identifies patterns within the data and develops what is called a learned model. The trained model can then apply those learned relationships to new information. For example, rather than waiting until an invoice becomes overdue, a machine learning system might estimate which invoices are most likely to become overdue. It could examine historical payment behavior, invoice size, customer characteristics, transaction history, and other relevant information. The result is usually not a guaranteed answer. It is a prediction, classification, or recommendation based on probability. This distinction is important. Conventional software follows explicitly defined instructions. Machine learning identifies patterns from data and applies them to new situations. However, AI does not operate independently of human design, data, objectives, and operating constraints. Its performance depends on the quality of the data, the design of the model, the objectives selected by people, and the context in which the system is used. Both approaches remain valuable. Conventional software is highly effective when the process is clearly defined. Machine learning becomes useful when relationships are too complex or numerous to describe through a simple set of rules. We have now established why AI matters, what the term means, and how it differs from conventional software. In the next section, we will trace the evolution of artificial intelligence, from symbolic rules and expert systems to machine learning, deep learning, foundation models, and today's large language models. Artificial intelligence may appear to have arrived suddenly with conversational systems such as ChatGPT, but the technology did not emerge overnight. Its development extends across more than 7 decades of research in mathematics, logic, computing, statistics, neuroscience, and information science. The foundations were established during the 1940s and early 1950s, when scientists began exploring whether machines could represent knowledge, solve problems, and imitate aspects of human reasoning. In 1956, a group of researchers met at Dartmouth College in the United States for what became known as the Dartmouth Summer Research Project on Artificial Intelligence. The term artificial intelligence was formally introduced there. This event is widely regarded as a foundational moment in the development of AI as a scientific field. However, the ambitions of the early researchers were far ahead of the computing power, data, and technical methods available at the time. Progress therefore occurred in stages. The field moved from systems based on symbols and explicitly programmed rules, to expert systems that captured specialist knowledge, to machine learning systems that identified patterns from data, to deep learning systems capable of working with images, speech, and language, and eventually to foundation models, generative AI, and emerging AI agents. The information processed by AI also became progressively richer. Early systems mainly worked with rules and symbols. Later systems processed structured data, such as numbers arranged in databases and spreadsheets. Deep learning systems expanded this capability to complex information such as photographs, speech recordings, and documents. Modern generative systems can work with language and content, and emerging agentic systems can increasingly interpret goals, use tools, and perform sequences of actions. This long history is important because it shows that today's AI systems are the result of many accumulated advances rather than one isolated invention. The earliest major approach is often described as symbolic AI. Symbolic AI represents knowledge through symbols, categories, relationships, and explicitly defined rules. For example, a system might represent a customer, an invoice, and a payment date as separate concepts. It could then use a logical rule such as, if the payment date has passed and no payment has been received, classify the invoice as overdue. The system processes these symbols according to rules created by human specialists. This approach is sometimes described as rule-based AI. It works particularly well when the problem is clearly defined, the relevant knowledge can be expressed through rules, and the environment does not change unpredictably. Expert systems developed this approach further. An expert system is an early form of AI designed to reproduce the decision process of a specialist within a narrow field. It normally contains 2 important components. The first is a knowledge base. A knowledge base is an organized collection of facts, rules, and specialist information. The second is an inference engine. An inference engine applies logical rules to the information in the knowledge base to produce a conclusion or recommendation. Consider a simplified medical example. If symptom A is present and test result B is positive, the system may recommend that diagnosis C should be considered. The system appears to reason because it follows a structured chain of logic, but its knowledge is limited to what people have explicitly placed inside it. When a situation falls outside those rules, the system may be unable to respond effectively. This became one of the central limitations of symbolic and expert system approaches. Real-world situations are often too complex, ambiguous, or variable to describe through an exhaustive collection of rules. Researchers therefore began looking for systems that could identify relationships directly from data. This led to the growing importance of machine learning. Machine learning is a branch of artificial intelligence in which algorithms learn patterns from data and use those patterns to make predictions, classifications, or decisions. A classification places information into a category. For example, an email may be classified as legitimate or as spam. A prediction estimates an unknown or future result. For example, a system may estimate future product demand or the likelihood that a customer will cancel a service. The central shift was significant. Instead of requiring people to describe every relevant rule, developers could provide the system with data from which relationships could be learned. Consider a spam filter. It would be extremely difficult to write a separate rule for every possible unwanted email. Spammers continually change their language, addresses, links, and techniques. A machine learning system can instead examine large numbers of messages previously identified as spam or legitimate communication. It can learn that certain combinations of words, links, sender characteristics, and message patterns are associated with unwanted email. It then applies those learned patterns to new messages. The same general approach can support demand forecasting, customer classification, fraud detection, risk assessment, and many other applications. The historical examples provide the evidence. The model learns patterns within that evidence. It then produces a prediction or classification for new information. Machine learning therefore changed AI from a field dominated by manually specified knowledge into one increasingly driven by data. To understand machine learning, it is useful to distinguish between two stages: training and inference. Training is the process through which a model learns from data. During training, the system is exposed to many examples. It makes an initial prediction. That prediction is compared with a known result or another learning objective. The model then adjusts its internal numerical values to reduce the difference between the predicted and desired outcome. These internal numerical values are known as parameters. A parameter is a value adjusted during training that influences how the model processes information and produces an output. A modern AI model may contain millions, billions, or even more parameters. Individually, these numbers do not represent complete ideas or facts. Collectively, they encode complex statistical relationships learned from the training data. The training process is repeated many times. As the parameters are adjusted, the model may gradually improve its performance. Once training is complete, the model can be used on new information. This stage is called inference. Inference is the process through which a trained model uses a new input to produce a prediction, classification, recommendation, or response. During training, a model may examine thousands of examples of historical payments. During inference, it may receive the details of one new invoice and estimate the likelihood of late payment. The important point is that learning does not imply consciousness, awareness, or human understanding. The system is not reflecting on its experiences in the way a person does. It is adjusting internal numerical relationships so that patterns in the data can be applied to new inputs. Its performance depends heavily on the quality and relevance of the training data. Incomplete, inaccurate, or unrepresentative data can produce unreliable results. As datasets grew and computing power improved, a specialized form of machine learning became increasingly important. This is known as deep learning. Deep learning uses artificial neural networks with multiple processing layers to identify complex patterns. An artificial neural network is a computing model composed of interconnected layers of processing units. These networks are loosely inspired by the structure of biological neural systems. However, the comparison should not be taken too literally. An artificial neural network is not an electronic human brain. It does not possess consciousness, lived experience, or human understanding. It is a mathematical system designed to process information and learn statistical relationships. The strength of deep learning lies in its ability to work with complex and unstructured data. Structured data is information organized according to a predefined format, such as rows and columns in a spreadsheet. Unstructured data includes documents, photographs, audio recordings, video, and other information that does not fit naturally into a fixed table. A deep learning system processes information through multiple layers. The early layers may identify relatively simple features. In an image, these might include edges, colors, or shapes. Later layers combine those features into higher-level representations such as objects, faces, or scenes. In speech processing, early layers may detect sound patterns. Higher layers may identify words, phrases, and meaning within context. In language applications, the system may identify relationships between words, sentences, subjects, and ideas. This layered processing has contributed to major advances in image recognition, speech processing, natural language applications, and autonomous systems. Deep learning is powerful, but it often requires substantial amounts of data, computing power, and energy. Its internal processes may also be difficult to interpret. We can now place these concepts into a clear hierarchy. Artificial intelligence is the broadest field. Within artificial intelligence is machine learning. Machine learning enables systems to identify patterns from data rather than relying entirely on explicitly programmed rules. Within machine learning is deep learning. Deep learning uses multi-layered neural networks to discover complex relationships, particularly within large volumes of unstructured data. Foundation models are large-scale models typically created using deep learning methods, and large language models are a category of foundation model focused primarily on processing and generating language. These terms should not be treated as competing technologies positioned beside one another. They represent nested relationships. Machine learning is part of artificial intelligence. Deep learning is part of machine learning. Foundation models are generally built using deep learning, and large language models sit within the broader category of foundation models. This hierarchy helps prevent a common misunderstanding. An LLM is an AI system, but not every AI system is an LLM. A demand forecasting model, an industrial inspection system, and a medical image classifier may all use artificial intelligence without being large language models. Traditional machine learning systems were often designed and trained for one specific task. A model created to detect fraudulent transactions would not normally be expected to translate a document or write software code. Foundation models introduced a broader approach. A foundation model is a large AI model trained on extensive and diverse data sets that can subsequently be adapted to perform many different tasks. The term foundation reflects the idea that one broadly trained model can provide a base for many applications. Training is often conducted using self-supervised learning. Self-supervised learning is a method through which a model learns from patterns and relationships within large datasets without requiring every example to be manually labeled by a person. For a language model, the system may learn by predicting missing or subsequent parts of text. Through repeated exposure to language, it develops statistical representations of words, grammar, subjects, styles, and relationships between ideas. Once trained, a foundation model can be adapted in several ways. The first is prompting. A prompt is an instruction, question, description, or set of information given to a generative AI system to guide its response. The second is retrieval of external information. Retrieval allows the model to draw on selected documents, databases, or other knowledge sources when generating an answer. This can make the response more relevant to a particular organization, project, or subject. The third is fine-tuning. Fine-tuning is the process of adapting a previously trained model to a particular task, field, organization, or type of data. A general model might therefore be adapted for legal analysis, healthcare documentation, scientific research, or customer support. Foundation models can support writing, summarization, classification, analysis, translation, code generation, and many other tasks. Some are designed mainly for language, others are multimodal. A multimodal model can process or generate more than one type of information, such as text, images, audio, video, or numerical data. This versatility distinguishes foundation models from older systems built for a single narrow purpose. A major breakthrough in the development of foundation models occurred in 2017 with the introduction of the transformer architecture. A transformer is a type of neural network architecture designed to process relationships between different pieces of information. Its central innovation is known as the attention mechanism. An attention mechanism helps the model determine which parts of an input are most relevant when interpreting information or producing an output. Consider the sentence, "The consultant submitted the report because it was due." To interpret the word "it," The model must identify that it most likely refers to the report. The relevant words are not necessarily beside one another. The model needs to examine relationships across the sentence. The attention mechanism allows it to assign greater importance to relevant connections and less importance to unrelated ones. This does not mean that the model understands the report, the consultant, or the deadline in the full human sense. It means that it has learned statistical relationships that help it interpret how words and ideas relate within context. Transformers made it possible to process language more effectively and at much greater scale. They significantly improved performance in translation, summarization, question answering, text generation, and many other language tasks. They also supported the development of models containing very large numbers of parameters and trained on enormous collections of text and other information. This architecture became the foundation of many modern large language models and generative AI systems. The evolution of artificial intelligence can therefore be understood as a gradual expansion in how machines represent and process information. Symbolic AI used explicitly defined rules. Expert systems applied specialist knowledge within narrow domains. Machine learning identified patterns from data. Deep learning used layered neural networks to process complex information. Foundation models created broadly trained systems adaptable to many tasks. And the transformer architecture greatly improved the ability of those models to process language and context. These developments prepared the way for large language models. In the next section, we will examine what an LLM is, how it generates a response, what it can do, and why natural language has fundamentally changed human-computer interaction. The developments we have examined, machine learning, deep learning, foundation models, and the transformer architecture, prepared the way for large language models. A large language model, usually shortened to LLM, is a type of foundation model trained on very large quantities of language data. Its purpose is to process, analyze, and generate human language. The word large refers to several aspects of the model. Large language models are trained on large collections of text and other information. They may also contain billions or even more internal parameters. As we discussed earlier, parameters are numerical values adjusted during training. Together, these values help the model represent complex statistical relationships within language. During training, an LLM may process books, articles, websites, reports, conversations, software code, and many other forms of text. This material is known as training data. Training data is the collection of examples used to teach a model to recognize patterns and produce outputs. The model is not simply storing every sentence as a searchable library. Instead, it learns statistical relationships between words, phrases, subjects, writing styles, and ideas. These relationships allow it to generate new responses when it receives an instruction or question. Before language enters the model, it is divided into smaller units called tokens. A token may be a complete word, part of a word, a number, or a punctuation mark. For example, a common word may be represented by one token, while a longer or less familiar word may be divided into several tokens. The model processes these tokens in relation to the surrounding context. Context refers to the information available to the model when it interprets an input and generates a response. This may include the user's question, earlier parts of the conversation, attached documents, system instructions, or retrieved information. The quality and completeness of that context can strongly influence the quality of the response. Large language models are probabilistic systems. This means they do not normally retrieve one predetermined answer from a fixed list. Instead, they estimate which token is most likely to come next, based on the input, the available context, and the patterns learned during training. Through this process, an LLM can answer questions, summarize documents, translate languages, analyze text, generate reports, and assist with many other language-based tasks. To understand this process more clearly, consider what happens when a user enters a prompt. A prompt is an instruction, question, description, or collection of information provided to a generative AI system to guide its response. The prompt may be simple: explain climate change, Or it may contain detailed instructions about the purpose, audience, format, tone, and information to be included. The first step is tokenization. The language in the prompt is divided into tokens that the model can process. The model then evaluates these tokens in relation to the available context. Using the relationships learned during training, it estimates the probability of several possible next tokens. It selects one, adds it to the developing response, and then repeats the process. The newly generated token becomes part of the context used to predict the next one. This happens rapidly, one token after another, until the response is complete. Imagine the model beginning the sentence, artificial. Several words could follow. It might estimate that intelligence is highly probable. After generating artificial intelligence, it evaluates what could come next. It may generate can, then help, then professionals, and continue building the sentence. At every stage, the next token is influenced by everything that has already appeared in the prompt and the response. The system is therefore not generating an entire answer in one step. It is constructing the response sequentially using probability and context. This process can produce language that is coherent, persuasive, and highly fluent. However, fluency is not the same as understanding. And fluency is not evidence of factual accuracy. An LLM can generate an answer that sounds convincing while containing errors, unsupported claims, or fabricated information. Such an incorrect but plausible response is sometimes called a hallucination. For this reason, AI-generated output should be treated as a draft recommendation or hypothesis until important information has been independently verified. The need for verification becomes especially important in fields such as healthcare, law, finance, engineering, public policy, and scientific research. The same underlying language capability can support a wide range of knowledge tasks. An LLM can answer questions by organizing relevant information into a response. It can summarize a long document by identifying and condensing its principal ideas. It can extract particular details such as names, dates, risks, actions, or financial figures. It can classify information by placing text into categories. It can translate material from one language into another. It can rewrite a passage for a different audience, tone, or level of complexity. It can generate new content, including reports, emails, proposals, presentations, and software code. It can compare documents, arguments, products, or alternative courses of action. And it can explain difficult concepts using simpler language, examples, or analogies. In professional work, these capabilities can produce many different outputs. An LLM can help prepare an executive summary from a long report. It can synthesize findings from several research documents. It can draft an email based on a set of instructions. It can develop a presentation outline. It can explain the meaning of data or describe patterns within a table. And it can assist software developers by generating, reviewing, or explaining code. These activities may appear to involve separate forms of intelligence, but they are applications of the same broad capability, processing patterns in language and information. The model does not become a lawyer when it summarizes a contract. It does not become a scientist when it reviews a research paper. And it does not become a software engineer when it generates code. It applies learned patterns to the information and instructions it receives. This distinction is important. LLMs can assist professionals, accelerate work, and expand access to knowledge. But their outputs still require human judgment, domain expertise, and verification. The most transformative aspect of large language models may not be any one task they perform. It may be the interface through which people can access those capabilities. For most of computing history, advanced use of computers required people to learn specialized methods of communication. Programmers used formal programming languages. Professionals worked through specialized applications. Users navigated menus, forms, buttons, and predefined commands. When a task required capabilities beyond the available software, a technical intermediary was often needed to design or program a solution. Natural language AI changes this relationship. Instead of learning a formal computer language, a person can increasingly describe a problem in ordinary words. The user can ask a question, request an explanation, refine the result, challenge an assumption, translate the output, change its structure, or continue the conversation until the response becomes more useful. This creates an iterative relationship between the person and the system. The first prompt does not have to produce the final answer. The user can provide more context, correct misunderstandings, ask for alternatives, and progressively improve the result. This change has widened access to advanced computing capabilities. Researchers can ask for help organizing literature. Teachers can develop explanations and assessments. Consultants can analyze information and structure recommendations. Lawyers can review documents. Doctors and healthcare professionals can organize knowledge subject to appropriate safeguards. Designers can explore concepts. Students can request explanations. Business leaders can examine options and prepare decisions. Natural language does not eliminate the need for expertise, but it reduces the technical barrier between human intention and computational capability. People can increasingly express what they are trying to accomplish without first translating every requirement into software commands. The interface has therefore evolved from requiring people to adapt themselves to machines towards systems that can respond more directly to human language. This is why large language models have changed human-computer interaction so significantly. They have made sophisticated computing capabilities accessible to a much wider professional and general audience. Large language models also provide part of the foundation for the next stage of AI development. This is the movement from generative AI towards agentic AI. Generative AI receives a prompt and produces an output. The output may be an answer, recommendation, document, image, design, or piece of software code. The interaction is usually centered on one request and one generated response, although the conversation may continue through further prompts. Agentic AI is designed around a goal rather than only an individual prompt. An AI agent is a system that can interpret a goal, gather information, plan a sequence of actions, use tools, and execute tasks with varying levels of human supervision. Consider the difference. A generative AI system might be asked, prepare a list of potential suppliers. It may generate a proposed list based on the information available to it. An agentic system might receive the broader goal, identify and evaluate potential suppliers for this project. The system may then break the goal into several steps. It might define selection criteria, search approved sources, collect information, organize the findings, compare suppliers, identify missing data, and prepare a recommendation. If connected to authorized tools, it may also enter information into a database, prepare draft communications, or initiate parts of a workflow. The agentic process can be represented as goal, plan, tools and information, actions, review, and result. The ability to review progress is important. An agent may examine whether an action produced the intended result and modify its next step accordingly. This creates a more dynamic workflow than a single prompt followed by a single output. However, greater capability also creates greater risk. An AI-generated paragraph can be reviewed before it is used. An agent connected to email, databases, financial systems, or operational software may be able to take actions that have real consequences. Human oversight must therefore be designed into the system. People should define the goal, authorize access, establish boundaries, review important decisions, and remain accountable for the outcome. Agentic AI should not be understood as removing humans from the process. Its value lies in coordinating multi-step work while operating within clearly defined limits and supervision. We can now bring together the central ideas from this video. First, artificial intelligence is a broad field, not a single application or product. It includes rule-based systems, predictive models, neural networks, generative systems, language models, multimodal models, and AI agents. Second, machine learning enables systems to identify patterns from data and apply those patterns to new information. This differs from conventional software, in which people explicitly define the rules for each clearly specified situation. Third, deep learning uses multi-layered neural networks to process complex information, including images, speech, documents, and language. Fourth, foundation models are trained broadly and can be adapted to perform many different tasks through prompting, retrieval, and fine-tuning. Large language models are foundation models designed primarily to process and generate language. And fifth, LLMs have made advanced computing capabilities more widely accessible by allowing people to interact with technology through natural language. The evolution can be understood as a progression. Early systems relied on rules. Machine learning enabled systems to learn patterns. Deep learning expanded their ability to process complex data. Foundation models created a base that could be adapted to many tasks. Large language models made natural language interaction possible at scale. And emerging AI agents are beginning to move from generating outputs towards planning and performing sequences of actions. AI did not become transformative simply because machines became more powerful. It became transformative because people could finally communicate with that power more directly. Natural language created a bridge between human intention and computational capability. That bridge has opened AI to professionals and individuals who may never have written software code, but who possess knowledge, experience, questions, and problems that computing can help them address. One useful question to test our understanding is, what distinguishes artificial intelligence, machine learning, and a large language model? Artificial intelligence is the broad field. Machine learning is one approach within that field that learns patterns from data. And a large language model is a type of foundation model built using machine learning and deep learning methods that specializes in processing and generating language. This completes our introduction to the foundations, evolution, and language technologies of artificial intelligence. In the next part, we will examine how AI creates value through its capabilities, its contribution to productivity, and its growing role in human-AI collaboration.